Today we're going to talk about matter and its states, the states of matter, its properties, and any sort of changes matter undergoes. We will finish right before we get to phase changes. On the asynchronous days, you will learn about separation techniques. But today we're going to just talk about matter generally. I'm going to go pretty quickly. It is a lot of vocabulary, so it's a lot of writing. So please pause the video as necessary. Make sure you're taking notes because you will be responsible for this on your test on October 2nd. October 1st and October 2nd. Okay, so what is matter? Well, matter is everything. Anything that occupies space and has mass is matter. Anything that occupies space and has mass. Those are the two things. You need to have some weight and you need to occupy space. There are 3 states of matter that we worry about in this class. Well, technically 4, but there's 3 states that we worry about in this class. As you get to more advanced chemistry classes, you'll talk about other states of matter, but the 3 that we talk about in this class, we have solids, we have liquids, we have gases, and the 4th one that we're not going to really talk about in this class, other than just mentioning it right now, is plasma. Okay, your solids, with solids, you've got your molecules all packed closely together and very organized. That's a solid. As you put some heat to it, so think of like a block of ice, as you put some heat to it, what's going to happen? Your ice is going to melt and you're going to become a liquid as you add heat to it. Then if you add a little more heat to that liquid, you're going to vaporize. You're going to become a gas, either via evaporation or via boiling. You'll become a gas. So block of ice, liquid water, water vapor. Those are your 3 states of matter we worry about. Okay, again, just to remind you, if you have a solid, if you add energy to it, enough energy, it takes more energy for certain things than others, you will turn things into a liquid. So you can turn a rock into liquid if you add enough heat, enough energy. It can take a lot, but you can do it. That's why we have molten lava. If you add more energy to your liquid, more heat, you become a gas. And if you add even more energy, you can become plasmas. That's like where your stars are. Okay? The state of matter changes as you add more energy. A lot of times that energy comes in the way of heat. Okay, so let's talk about what a solid is. A solid is a form of matter, a type of matter that has its own definite shape and volume. So if you have a block of ice, it's going to take up a certain amount of space, a defined amount of space, and it's going to have its own shape. Okay, so it's going to have its own shape and it's going to take up a defined amount of space or volume. Okay, a liquid, it's going to have flow. So it has its own volume. The volume doesn't change, but it's going to, because it flows, it can take the shape of a container. So if you have a little teeny tiny cup and a bucket and the same amount of water, the water is going to take up the space in the bucket. It's going to be very shallow, but in a teeny cup, it'll look less shallow because it's taking the shape of the container. Your gases don't have their own shape, and they also don't have their own volume. They're going to take the space, the shape of the container, and they're going to fill the entire volume of its container. So that means that gases, those gas molecules don't want to be near each other. So they're going to say, okay, I've got this much space available to me. I've got a room where I can fill up. And I'm going to try to maximize the separation between each individual molecule. So gases are going to take up the space. It's going to fill up the entire volume of a container. Okay. As you decrease the container size, then those molecules get closer together. As they get closer together, they're going to start vibrating, hitting each other. And that's when you have things that have a little bit more pressure because those gas molecules are hitting each other. Okay. Then you've got plasma, just so you know what it is. It's like an ionized gas. Ionized means that it has a charge. It's a gas where ions and electrons coexist. Okay, so like something like sun, some stars, great big ball of plasma, a lot of gas, a lot of energy, a lot of movement. But we don't worry about that in this class. It's beyond the scope of this class. Okay, so matter can be defined into, there's 3 classes of matter. We have mixtures, we have elements, and we have compounds. Matter is made up of 3 things. You can have elements, you can have compounds and we can have mixtures. These two kind of go together, and this is its own little beast. So we're going to talk about those individually. Okay. So again, matter is mixtures, compounds, and elements. Okay. So matter can be divided into pure substances, and that would be the elements and the compounds. Pure substances are elements and compounds, and then mixtures. And those can be what's called heterogeneous and homogeneous. We're going to start with the pure substances. So matter, again, are elements, compounds, and mixtures. But these two, elements and compounds, are pure substances. So what are elements? Elements are the simplest form of matter. Remember, something that takes space and has weight that can exist under normal laboratory conditions. Okay, so it's got the word element. So that would be something off the periodic table of elements. It's the things that you see on the periodic table by themselves. They're represented by 1 or 2 letter chemical symbol. So something like Na, that is sodium. S, that is sulfur. K, that is potassium. Ag, that's silver. These are straight off the periodic table. They are not chemically combined with anything else. An element is the simplest form of matter that is not chemically combined with anything else. And that's considered a pure substance. The other pure substance would be something like a compound. A compound is something that is chemically combined. So substances that can be separated into simpler substances only by chemical means. Things that are chemically combined, so if they're chemically combined, to separate them, you need to use chemical means. Something like NaCl. So up here for elements, sodium was an element by itself. But when it's combined with chlorine, sodium chloride, that's table salt, that is now considered a compound because they're chemically combined. In order to get sodium out of this thing, out of sodium chloride, you have to use chemical means to break this bond. Same thing with water. This is a compound because it's made up of 2 hydrogens and 1 oxygen that are chemically combined, held together by a covalent bond. In order to get the oxygen back out, you must chemically separate them. You must break a bond. So an element is something straight off the periodic table. A compound is something that is chemically combined. Okay, so something like an element would be something like helium atoms, either just like little individual dots, or oxygen. Oxygen doesn't exist by itself. It always exists. It exists combined with each other. Those are called diatomics. We'll learn about that later. So an element would be like helium or oxygen. Those are elements because it's just one thing, just helium, just oxygen. A compound would be something like water. The blue being, in this case, the blue being hydrogen and the red being oxygen. Okay, those are compounds. Okay, so that takes care of this part of the matter, right? The pure substances, the elements and the compounds. So what are considered mixtures? So mixtures are a physical blend, physical. Remember the other thing we talked about, compounds, was chemical blend. Now we're talking a physical blend of 2 or more substances. So like a dinner salad, that is a mixture. You've got some lettuce, you got some croutons, you got some salad dressing, you might have a little cheese, a little spinach, some chicken. That's a mixture. It's a physical blend of 2 or more substances. Salt water is also a mixture. It's a mixture of salt that has been dissolved in water. It's not a chemical reaction. The salt has been dissolved. And you can get the salt back out of that water. If you evaporate the water, you'll be left with salt. It is a mixture. Okay? So a mixture can be separated by physical methods, where a compound cannot. Remember, we said if we want to get the hydrogen out of the water, you have to have chemical means to separate them. A mixture is the opposite. A mixture is a physical blend. So in other words, if you want to separate them, you use physical methods. And that's what you're going to be learning about, these physical methods. You're going to be learning about that during your asynchronous days later in the week. Okay, so these mixtures can then further be divided into 2 groups. You can have what's called a heterogeneous mixture, and you can have something called a homogeneous mixture. Okay, heterogeneous and homogeneous. Okay, a heterogeneous is let's look at the root word, hetero, that means different. So a heterogeneous mixture is a mixture that is not uniform in composition. In other words, it's different, it looks different. So a salad would be a perfect example of a heterogeneous mixture because because it's got lettuce and it's got croutons and it's got salad dressing. And you can see all those things with your eye. It's a mixture. They're mixed together. They're not chemically combined. You can see it's not uniform. Okay. A homogeneous mixture is a mixture that is completely uniform in composition. So something like salt water. If you look at a cup of salt water, you can't see the salt. You can't separate the salt from the water with your eyes. You can separate them physically later, but you can't tell the difference between them. So it's a uniform composition. Okay? So a heterogeneous, again, something like a salad, is a mixture with an uneven texture. And those components of the mixture can be detected with the eyes. Your eyes can see all the different individual parts. Something like a chocolate chip cookie is a heterogeneous mixture. You can see the chocolate chips apart from the dough. The dough is homogeneous, but the chocolate chips from the dough is heterogeneous. Chex Mix. You can see the Chex, you can see the pretzels, you can see the little, I don't know what these are called, bagel chips. That's a heterogeneous mixture. If you got like a little lava lamp or you put oil and water, you can see the oil and the water, oil and vinegar. Let's say you can see the oil and the vinegar, or you can see the oil and the water. You can see the different parts. They're mixed together. That's called a suspension. We'll talk about that in a little bit, but you can pick out the different parts with your eyes. A slice of pizza, that's heterogeneous as well, because you can pick out the pepperonis. You can go and pick out all the olives, because olives don't belong on a pizza. It's a heterogeneous mixture. This is your red blood cells. These are your cells. You can pick out all the different parts for your cells. Okay, M&Ms. You can take out all the green ones and eat those first, and take out all the blue ones because blue's weird for M&Ms. They didn't have blue ones when I was growing up. So you can pick all those out individually. It is a heterogeneous mixture. Remember, hetero means different. It's uneven composition. Hey, if you're eating some Heart Smart cereal, you can pick out the little marshmallows from the cereal. Put the marshmallows along on the side because those are gross. Okay, so homogeneous mixtures are a uniform mixture at the particulate level that consists of two or more substances in the same phase. What does it mean to be in the same phase? Both, like the two or more substances are in all liquids. They're all solids. They're all gases. Okay? So they're often referred to as solutions. If you have a homogeneous mixture, it's often referred to as a solution. So an example of a homogeneous mixture would be your coffee. Your coffee has water in it, and it's got whatever coffee's made up. It's got a caffeine. It's got all these things. But if you look at a cup of coffee, if you look at it, you can't tell where the caffeine is and where the water is and where the coffee is. Okay, it's a homogeneous mixture. If you're looking at a glass of non-pulpy orange juice, okay, you can't tell where the citric acid is. You can't tell where the fructose is. You can't tell where the water is, but it's all in there. It is mixed in a homogeneous manner. Okay, it's homogenized. Okay, if you have you can also have homogeneous mixtures of solids. Those are called alloys. So something like brass or 14 karat gold is an alloy. So the way you make a solid phase homogeneous mixture, an alloy, is that you get these solids and you melt them. You make them a liquid and you mix them really, really well, and then you let them cool down, and now you have a homogeneous mixture of a solid, and that's called an alloy. So a homogeneous mixture a lot of times is referred to as a solution, but if it's specifically a homogeneous mixture of a solid, it is called an alloy. The word solution is typically used for liquid mixture, homogeneous mixtures. Okay. Here we've got some water, and I'm not sure what's in here, but the point is that you can't tell what it is. It just looks like liquid. You can't tell if there's some molecules in there. Okay. Let's do some examples. So if you have Kool-Aid, you guys even drink Kool-Aid anymore? If you have Kool-Aid or fruit punch or one of your like juice boxes, you can't tell where the sugar is, but you know there's a ton of sugar in there, and the food coloring and the fruit juice and all those things. You can't tell, you can't separate them. It's a homogeneous mixture. Salt water, homogeneous mixture. Sugar water, homogeneous mixture. The air we breathe, like clean air that we breathe on a really clean day, That's a homogeneous mixture. You're surrounded by nitrogen, right? 78% of the air around you is nitrogen. 21% of the air around you is oxygen. But can you see the nitrogen molecules? Can you see the oxygen molecules? Can you see the CO2 that you are breathing? Can you see the carbon monoxide that's out there, or the NO or the NO2 that's coming out of that's in the air? You can't see those things, but it's there. It is a homogeneous mixture of gases. Salt water, sugar water, those are homogeneous mixtures. Air is a homogeneous mixture. Alloys are homogeneous mixtures. Now you've got a suspension. That's like oil and vinegar. That's a heterogeneous mixture that can settle to the bottom. You make a separation. You can mix it, but then it separates. It's called a suspension. Okay, something like a salad dressing. Okay, so just to remind you, your matter can be divided up into elements, compounds, and mixtures. Your elements and your compounds are pure substances. Your mixtures can be either heterogeneous or homogeneous. Okay. Let's look at these. Let's look at these representations. So let's look at number one. So what does this look like? You want to tell me if this is a pure substance? If it's a pure substance, is it an element or a compound? If it's not a pure substance, is it a mixture? And what's it a mixture of? So let's look at number one. And number one, you've got, let's look at each of these little circles, each of these little things together. So you've got two whites and one black. This is a compound. This is a bunch of compounds. Okay, just a compound because it's just the same thing over and over and over again. This is probably water. Now, if you look over here, you've got these individual, like you got a bunch of white ones, you got a bunch of black ones. Okay, white and black. If this is not chemically combined to anything, those guys are elements. But we have several different elements. So this is a mixture, but specifically, this is a mixture of elements. Mixture of elements, like the air we breathe. Nitrogen and oxygen, let's say. Okay, now let's look over here. Well, we've got some of these things like that look similar to these. So those are compounds. We got a bunch of those. And here we have some, these are what's called a element because it's the same guy together. See, they're the same guy together. So this is a mixture also, specifically of elements, like the two white things, and compounds. Okay. Now let's look at number four. Number four, this is a compound, this is a compound, this is a compound, this is a compound. This is a different compound. Okay, so this is also a mixture, but this is a mixture of compounds. Okay, now here we've got a bunch of just little black dots. Those are just elements. And here, this looks similar to this guy over here, except for it's a different compound, but those are just compounds. Okay, so you're gonna learn in your asynchronous days how to separate mixtures, these heterogeneous and homogeneous things. How do you separate them? And because they are a physical blend, you use physical processes. So just look out for that Nearpod, which will be available to you on Wednesday. We're not going to run through this because this is in your Nearpod, but you should go through it. You should go through it in the Nearpod. Okay. So going back to your pure substances, your elements, your compounds, they have a unique set of physical and chemical properties. All substances have a unique chemical and physical property. No two substances, different substances, will behave exactly the same. They might behave in a similar fashion, and the periodic table tells you how they'll behave, but they're not exactly the same. That every single oxygen atom will behave the same way. Every single water atom, a molecule, will behave the same. Every single helium will behave the same, but water and helium will behave differently. And those are a unique set of physical and chemical properties. So let's talk about what that means. Physical properties are properties that can be measured or observed without changing the identity or composition of a substance. This is like the soul of the substance. Okay, you can observe it or measure it, but you're not changing what it is. Okay, the chemical makeup is not changing when these properties are observed. For example, the color. You can observe the color of something, and it's not going to change as you observe it. If it's changing, something else happened. You can observe, you can smell what a chemical smells like. You smelling it doesn't change the fact that it is gasoline. The texture does not change when you observe it. How it tastes, the temperature at which it freezes. Water always freezes at 0 degrees Celsius, always. Okay? The temperature at which it melts, same thing as the freezing point is the melting point. The temperature at which it boils, 100 degrees Celsius. The density, the mass per volume, how much it weighs, how hard it is. Those things are physical properties. They do not change with your observation of them, as opposed to chemical properties. These properties indicate how a substance reacts. That's the key word, reacts with other substances. These are only observed when the substance undergoes a chemical change. Undergoes a chemical change. Your chemical properties are how something reacts. Your physical property is its soul. Chemical property is how it reacts. When you put it in a situation, how does it react? Okay. For example, is it flammable? The only way you're going to know if something is flammable is if you light it on fire. Does it light on fire? Is it flammable? And once it lights on fire, you've had a chemical reaction. You've changed what that is. Is it combustible? Does it blow up? Can it burn? Does it react with? These are all signs of chemical properties. So how do you distinguish between chemical and physical properties? Again, physical properties are characteristics that can be observed or measured without changing the sample's composition, what it looks like, how you're not changing the sample's composition. Chemical properties is you're changing the substance's composition. For instance, HCl is soluble in water. The fact that you can dissolve hydrochloric acid in water is a physical property. It's not a chemical reaction. It's just you're dissolving it. You're just putting it in there and it's mixing in really, really well. So HCl is still in that water. It didn't react, but it was soluble. That is a physical property. We did not change HCl. The fact that HCl is corrosive to metals, that means it reacts with the metal. That's a chemical property. The fact that it'll make something rust, it's a chemical property. HCl burns the skin. Anytime you're burning anything, you have a chemical reaction. So the fact that HCl burns skin, hydrochloric acid burns skin, that is a chemical property. Okay. So example, let's look at water. Let's look at some of its physical properties and let's look at some of its chemical properties. Physical properties, it has no color. It's colorless. That's a physical property. It has no smell. If you're at room temperature, it's a liquid. It has really no taste. It always freezes at 0 degrees. It always boils at 100 degrees. You're not changing water when you go from water is still water when it's an ice cube, when it's liquid water, or when it's water vapor, it's still water. You're not changing what it is. The fact that it can flow, that has to do with something called hydrogen bonding. We've got chemical properties for water. Water reacts with baking soda, right? You get little bubbles, right? That is a chemical property. The fact that it reacts with baking soda, the fact that water can react with acids. And that's a chemical property. Does not react with oil. Chemical property. Water is not flammable. That is a chemical property. Okay. So these physical properties can also be categorized further. A physical property can be categorized as either what's called intensive or extensive, sometimes called intrinsic or extrinsic. Okay, I'll try to use the word extensive and intensive just to be consistent, but if you see those other words, it means the same thing. Okay, so intensive properties are properties that do not depend on the amount of matter present. They don't, again, we're talking about physical properties. They don't depend on the amount of matter present. So if you have something and it's blue, it's always going to be blue. It doesn't matter how much of it you have, it's blue. what it smells like. Water always has the same non-odor. Doesn't matter how much water you have, doesn't have an odor. Conductivity, that means how likely you are to be able to run a current through it. If something is non-conductive, doesn't matter if you have a lot of it or a little of it, it's not going to conduct electricity. Hardness, how hard something is. Doesn't matter if you have a lot or a little, the hardness doesn't change. Those do not depend on the amount of matter present. Whether you have a bucket of water, or a bucket of ice, or you have an ice cube, it's always going to freeze at 0 degrees. Doesn't matter how much water you have, it's always going to freeze at 0 degrees. It's always going to boil at 100 degrees Celsius, always. Doesn't matter how much you have, whether you have a bucket full or bathtub full or a little thimble full, it's still going to boil at that temperature. It won't boil before then. Okay. The density, how many grams per milliliter of water there is. That's not going to change depending on the amount of matter present. These are all what's called intensive properties. Not to be confused with extensive properties. Those are properties that do depend on the amount of matter present. Okay, it's external to the matter. Things like mass, how much something weighs, how long it is. Those depend on the mass. Your mass, the mass of your water is going to change whether you have a bucket or a little thimble size. It's going to weigh a different amount. That's extensive or extrinsic. Okay. How much space it takes is going to depend on the matter present. Those are extensive. How much what its length is. Those sort of things are extensive. Okay. Now let's talk about density. Density is one of these physical properties of matter. You've learned about density since middle school. No, since elementary school. Okay. Density shows how tightly matter is packed within an object. Okay. How close are those molecules packed together? So if you look at this here, this guy right here is more dense than that one. So if you're looking at a certain volume, okay, the mass of this is going to be less than the mass of this per the same volume. Density is grams per volume. This guy is going to have a lower density, grams per milliliter, than this guy, grams per milliliter. Okay, it shows how tightly matter is packed within an object. Okay. The density of water, which you should know, but it's easy number to remember, is 1 gram per milliliter. 1 gram per milliliter. Anything that has a density greater than 1 gram per milliliter is going to sink in water because it's heavier. It's heavier. Anything that has a density less than 1 gram per milliliter will float in water. Okay? And if you have the same density, you're going to be kind of just suspended in it. Another physical property of matter we can talk about is viscosity. Viscosity is the measure of a material's resistance to flow. So if you think about it, think about water and ketchup, or water and maple syrup or syrup. Water, they're both liquids, correct? But water flows much easier than maple syrup or much easier than ketchup. Okay? Here, ketchup has a higher viscosity because it is resisting that flow. Those molecules aren't sliding as well over each other in order to flow. They're both liquids, but one is more viscous than the other. Okay, so again, this is how we're going to break up our matter properties, our properties of matter. The first thing you're going to ask yourself is, are these properties determined without changing the identity of the substance? If you are changing the identity of the substance, you have now, these are now chemical properties. You change the identity, you are a chemical property. So then you ask yourself, how does the substance react in the presence of air? You can ask, how does it react in the presence of acid, water, base? What other chemicals? What happens if it's heated? These are all things you ask yourself in terms of its chemical properties. Okay, so let's say instead of answering no to the question, are these properties determined without changing the identity of the substance, If the answer is yes, then you're talking about physical properties. And those physical properties can be divided into intensive properties and extensive properties. So let's talk about the intensive again. Those are the ones that do not depend on the amount, the color, the taste, temperature it melts, temperature it boils, its density, its luster. That means how shiny it is, how hard it is. Those don't depend on how much you have. Or you've got your extensive properties, your mass, your volume, your length, its shape. Those are extensive properties, and it's going to depend on the size. It's depend on the amount of stuff you have. Okay. So we talked about properties, but now let's talk about what do physical changes look like. So a physical change is a change that alters a substance or appearance without changing its composition. You're changing what it looks like, but without changing its composition. So changes in state would be an example of a physical change. Melting, your ice cube melting. It's still water, but now instead of being a solid, it's now liquid. It's a physical change. It's not a chemical change, it's still water, but you've changed what it looks like. So a change in your state. Going freezing, so the other way, going from a liquid to a solid, you're changing your state. Boiling, going from a liquid to a gas. Condensing, that's going from a gas to a liquid. That's what happens when like water condenses on your cup, on your glass. Vaporizing, that's like evaporation when you're going from a liquid to a gas. Subliming, this is when you're going from a solid to a gas. This is what dry ice does. Now that Halloween's coming around the corner, this is what dry ice does. You have a big block of dry ice, and it skips that liquid stage. It goes straight from a solid to a gas. That's called sublimation. Okay. Other things that are physical changes are cutting a piece of paper, cutting a tube of, I don't know, toothpaste. That's you're changing its physical appearance, but it's still a physical change. You're not changing what it is. You're not changing its composition. Bending something. You have a wire and you bend it. It's still the same wire. It's still made of the same stuff. You just bent it. Breaking it, right? Just tearing a piece of paper, breaking it, pulverizing it. That's making it into a powder. It's still the same stuff. You've just really pulverized it. Okay, those are all physical changes. Those are all signs of a physical change. So what does a chemical change look like? Chemical changes are reactions. They're chemical reactions. Okay, so one or more substances are going to react to form new substances with different chemical and physical properties. You're making something new. You're starting with one thing and you're ending with something new. The something new is going to behave differently than the original thing. It's going to have different physical properties. It's going to melt at a different temperature. It's going to boil at a different temperature. It's going to have a different color. It's going to have a different odor. Many things. Reactivity is going to be different. Okay. The beginning substance is different than the ending substance. This is a chemical change. Okay. For instance, rusting. When something rusts, it's because you had a chemical change. You have an oxidation occurring. When something burns, when something's burning a flame, that is a sign of a chemical change. Something gets corroded. Digestion, you're turning the food that you ate into some energy, something useful for your body, and then you have waste. That is a chemical change. The fact that you can breathe, that is, you're breathing in oxygen, and what do you breathe out? Carbon dioxide. Where did that carbon dioxide come from? A chemical change in your body while you're breathing. Decaying, things decaying on, you got some roadkill, let's say, and it decays on the side of the road. That is a chemical change. Okay. Chemical changes, chemical reactions can be described by chemical equations. You're going to have on the left side, you're going to have what's called your reactants, the things you started with, the things that are reacting together, and you're going to make a product. That little arrow, we call that yield. So we're going to say the reactants yield the product. Okay, for instance, iron plus oxygen. This is rust. Iron plus oxygen, giving you iron 3 oxide. This guy is rust. Okay, and it occurs with iron gets exposed to oxygen. Okay, this is a symbol for iron. This is oxygen. You're making iron 3 oxide. Okay. This is a chemical equation. So just remember, when you're doing these things, you need to remember the law of conservation of mass. In any chemical and physical change, matter cannot be created nor destroyed. Okay? You can't make something heavier. You can't make something lighter. You have to conserve the mass. It might seem lighter because you lost something to gas and that escaped, but the point is that you have to conserve mass. And we're going to use this concept a lot when we get to stoichiometry unit. Okay? The mass of your reactants, the stuff that you started, must equal to the mass of your products. So if you have hydrogen plus oxygen to give you water, if you have 10 grams of hydrogen and you have 5 grams of oxygen, your final weight of water has to be 15 grams total because you can't make or destroy anything. So what are signs that a chemical change occurred? How do you know that a chemical change occurred? What if the color didn't change at all? How do you know? Well, evidence of chemical change are the following. If you see gas bubbles, if there's gas bubbles now where there wasn't gas bubbles before, you know what? You probably produced a gas in a chemical reaction and gas evolved and now it's escaping to the air. So if you see little gas bubbles where there wasn't gas bubbles before, then a chemical change happened, a chemical reaction happened. If you see a precipitate or a solid form, so you've mixed a couple things and all of a sudden you see a solid at the bottom of your test tube, let's say, where there was no solid before, that is a sign of a chemical change. These are also things that when we're talking about chemical reactions, we're going to talk about what motivates a reaction to happen. What is the motivating factor for these reactions to happen? Motivating factors is you're going to form a gas. That's a motivation for a reaction to happen. You're going to form a precipitate. That's a motivation because these guys you can get at a lower energy state. Now, another huge sign of a chemical change is heat. Did it all of a sudden get hotter? Did it all of a sudden get colder? Was heat released? Was heat absorbed? Those are signs of chemical changes. Did all of a sudden you see a little burst of light? That's a sign of a chemical change. Light doesn't just occur. There has to be a reason for it, a chemical change. Was there a change in color? So color is a physical property. If all of a sudden the color changed, you've made something new, because if it was red to begin with and now it's blue, then it's not the original thing. It is now it's now a new thing with a new physical property. You've made something new. It is evidence of a chemical change. Okay, now let's go back to this heat released and heat absorbed. You have something called exothermic reactions. Exothermic reactions is when heat is released. So exiting. Heat is exiting the reaction. So it feels warm to the touch. Heat is feeling warm. It feels warm to the touch. An exothermic reaction is one where heat is released. The majority of reactions are going to be if they're going to release heat, they're going to be exothermic. The majority of the reactions, not all, but the majority. A fire burning. You sit next to a fire and you put your hands up next to it. That is an exothermic reaction. You're feeling heat. Okay, not to be confused with an endothermic reaction. Endothermic reaction. That's where the reaction is absorbing heat. So if it's absorbing heat, it's going to feel cold to you because it's taking heat away from you. So an example of that would be when you get hurt out on the football field, let's say, or out on the dance stage or wherever, and you need an ice pack, and there's those little ice packs that you kind of like crack, and then all of a sudden it gets really, really cold. And what you're doing when you crack it is you're breaking a barrier, and you're combining two things that form an endothermic reaction where it gets cold and you make a little ice pack. So these are evidence of chemical changes. And exothermic means heat released, and endothermic means heat absorbed. Heat is entering, endo, so it's cold. Heat is exiting, so it's warm. This is where we're going to end today. So on the asynchronous stage, you're going to learn about how to separate things, how to separate mixtures with physical means. You're going to learn all the different separation techniques. You will have an assignment you will have to do that will be due on Sunday night. And I look forward to seeing you after that's done.